Okay, so hopefully the connection is a bit more stable now. So this is a new attempt. Okay, so I was about to explain about the contact detection method based on bounding boxes. Now, what's the deal with the bounding boxes? Well, as the title implies, this is a method that is based on the boxes. And we're going to have a very different size of boxes. And how it goes is that we have the big boxes, and the big boxes are surrounded the big objects. And just to give you an example, this is a harbor crane, or part of the harbor crane that is used to move containers from harbor to ship. You know, this particular component, hopefully, yeah, I can see that you see my pointer. This is actually the device that is connecting itself to container itself. And now, what happens in the bounding box modeling is that this particular device is within the one big box, and this one big box is called root level box. And then there is a similar size, I mean even bigger than that, big boxes that are, say, surrounded by, or is put in a modeling world in such the way that the entire ship could be within the box. And now, then it's about to compare whether or not these root level boxes are colliding. And now, because we are looking at the box colliding possibilities, it is easy to check whether or not these big boxes are colliding. And not, let's say that hypothetically, yes, two boxes are colliding. So the big box that is such that this connecting device is inside of the box, and the ship box, they are colliding. What happened next is that you're going to move on to branch level boxes. And the branch level boxes, well, of course, like you pretty much guessed it already, are much smaller boxes, such that there may be a box that it is under this particular flap that it is used to do the connection itself. There may be another box like the one that is shown here, which is looking if there is this particular part of the disconnecting device is under connection or is contacting to another bodies. So then how it then goes is that you see the root level boxes are penetrating, so there is a collision between the root level boxes. You're moving on the branch level boxes, and you see whether or not these smaller boxes are now contacting or penetrating. And even if that's the case, then you're moving the final level, which is usually the joint primitives, and that's the leaf level. And that's kind of like moving from the root, branch, to leaves, and now if the leaves are contacting, this is where you know that the real contact takes place. And an example how that works out in a rally game, the rally car itself could be inside of the big box. That will be root level box. Then there could be both sides of the road, they could be surrounded by big boxes. And now if you're making mistakes in your steering, you start to go a little off from the road. That's when you can actually start looking that, okay, the root levels are contacting. You're moving on the branch level. The branch level could be your front fender and how that is against the tree. And now it looked at, okay, yes, there is a possibility that the fender is attached in the tree. Then you're moving the leaf level, which is a joint primitives. You actually see if these two graphics are colliding, and yes, if they are colliding, then you know, okay, that's it. Then you know where the contact will take place, and then you are ready to move on to contact event modeling. So that's how it goes. And now, as I mentioned, there are many varieties in bounding box method. Pretty much the varieties are coming from the fact how the object inside of the box is oriented, and how one can place the component inside of the boxes. So we have a method that is called oriented bounding box, and we have axis aligned bounding boxes. So these are, as I mentioned, the difference is coming from the fact that how the body itself can be within these boxes or inside of the boxes. I don't think that these are really important us to know in details, but
Biomechanics is a little bit the same thing.
it's mentioned here that this axis-aligned bounding box is something that is coarse and fast, CPU efficient, but both are used. It really depends on the application which one makes sense to use. This time is enough for you to know that there are varieties in the bounding box method, and these varieties are coming from the fact how the objective is within these boxes. So this is oriented bounding box, this is axis aligned bounding boxes, so this is a difference. Now, once the contact detection is carried out and we figure it out, yes, there is a contact that takes a place. We need to move on this a bit because it somehow moved a bit left. I don't understand why that happened. Anyway, so it could be a little right. Okay, so what happens next? So we're moving on to contact event itself. And of course, if we would deal with the deformable bodies, let's say if we would deal with models that are all made by using a finite element method, then it becomes easy because you just say that, okay, two bodies cannot penetrate each other, and because of the deformation, the real contact forces can be predicted very accurately. And that's what's the case in when one is modeling in gear systems. Like example is here, the two gears are contacting, and locally what happens is that you just preventing the penetration here, and then the forces will be accurate. Then also we're going to discuss a little bit because the deformation itself will be according to reality. Well, it's clear that this is not very practical method if we're speaking about very high number of possible contacts, so if we're speaking about many practical applications such like real-time simulation. Of course, this is not going to be possible to do it because modeling all bodies as a flexible bodies, that's going to be too demanding computationally, so this is not the realistic option. So what we need to do then is that we need to look at how the rigid bodies can be contacting each other and how the contact even in case of rigid bodies can be carried out. And in that we have, roughly speaking, two approaches. Very common one, very often used, is a penalty force approach, and as the title implies, this is a method where we're using forces to separate the bodies each other. So if I'm taking again this phone and this case, so basically when they are colliding, I'm using artificial force to separate these bodies. So basically there will be a force component that will push them away from each other, and this force method is called penalty force method. And this is very often used, very common in many applications, and it's there's many varieties on that. Now its alternative is the one that is called cone complementary approach, which is completely different concept. And it's completely different concept because that will be based on kind of constraint equation. But the constraint equation will be unequal constraints. And we will get back to that after explaining this penalty force method to you. Now the penalty force method is all about indentation. It's about allowing two rigid bodies to penetrate, to overlap, which of course in reality is not something that takes place, but this method is assuming that, or is actually allowing two rigid bodies to overlap. And now what happens in the penalty force method is that this overlapping will be measured, and it will be measured as, you know, here the X is measuring how far this ball is penetrating to this rectangular body. Let's say that the rectangular body is a crown body, and the ball is coming from top of this crown body. So how far or how this can penetrate to this crown body and this will be measured from the factor that is called penetration factor.
So there's a lot of computing to look.
Then what follows is that we're simply introducing a force that is a function of the penetration. And now there is many different varieties how that can be carried out in practice. But basically it goes such the way that we are assuming these two objects to have a stiffness some kind. And this stiffness of course depends on the parameters that the one is defining, or how this we are assuming the material to behave. And now then this stiffness is multiplied by penetration. This is the one that we're measuring from the previous figure. So x is missing here, which is a little bit confusing, but x is the one here. So as the penetration becomes higher, depending on the stiffness value, the force becomes easily very big. Now then we have here this penetration power n. The power n is typically a number that is other than 1. So it's not usually behaving in a linear manner, but a little bit of progressive manner. And it's behaving a little bit of progressive manner because if this power is equal to 1, then there is a
contact even model. And now how to carry out that, I will introduce two different ways to make that happen. But prior to that, let's take a look at the contact detection. And the contact detection, I mentioned that there is
I got the information that I have a very annoying echo. Let me find it out.
Very often used in a chem technology. Also in a multibody system dynamics.
Yeah, that's very bad. That's not acceptable, of course.
Bounding box method.
Of course not. Let me see. Where the heck the echo could come then? Because I can see that the camera is muted. Okay, so it's already gone. Okay, Yona, can you please let me know if this is a problem in the future as well? Because, of course, I don't hear myself. So what I did was that I was just tuning my audio settings here in OBS. Okay, so I hope that it is alright now. Okay. So I was about to explain this penalty force method and how the penetration is power n. Usually n is not 1, meaning that linear penalty force with respect to penetration, and it is not linear but progressive, because the problem in the linear connection is that when you look at that, there is no forces at all, which is moving from this curve here a little left from the origin. That's obviously when there is no forces at all. And when you hit it to penetration, or when the penetration start to increase, there's a discontinuity in the origin. And this discontinuity can be very annoying in terms of computation, because everything is, roughly speaking, everything is about how to compute the derivations, and here there will be discontinuity part, and you want to avoid the discontinuities as much as you can. Another difference is this: when you're moving here to left, you have a smooth connection, so it's not jumping, or it's not having the radical rapid change, but instead it's having the smooth curve like this. And of course this is computationally way more beneficial comparing the situation when this is equal to 1. Okay, so of course there's many varieties in these equations, and these are just showing that how the forces can be are computed as a function of penetration, well, there is no surprises, of course, because of course, if it is linear, then it's behaving like that. If the power is 1.2, then it's behaving a little bit of progressive way. When it is 2.2, the progressivity becomes higher, and finally when it is 3, it's a highly progressive. This is just an example. Usually when you look at these penalty force methods that are introduced in the literature, it is typical that there is something added to this penalty force. I mean, stiffness multiplied by penetration. Usually the components that are added here are stiffness and other matters that are smoothing down the behavior. So that's a typical scenario, but here we don't really care about that. Here's an example. So this example is about how to use this penalty forces in order to predict how is contact forces in a ball bearing. And now how this goes is that this is a multibody simulation where we actually have here inner ring and we have an outer ring, but we do not have the real balls here. So the balls are just visual representation, but they don't have any inertias here. But what we do is that we are assuming them to have a certain geometry, and based on the geometry we are able to compute how much is a reaction force is associated to each one of these balls. And these reaction forces are computed using this penalty force approach. And how it goes in details, of course there's quite a bit of details, but roughly speaking this tells you how is a penalty force computing. So we have stiffness that is coming from the material parameters, and then we have here penetration that is coming from the geometrical computing, and then we have here n, which this particular case is 1.5, and it well corresponds to situation in the ball bearings. So again, stiffness coming from a little bit about the geometry, but mainly from the material, and then this one is here computed based on how the bearing itself behaves. And this gives us the forces that are then placed in the multi-body model, and this comes even with the user interface, such the user can put the dimension on the top of the bearing from the database or create the database by itself, and then so it goes such that you put in some graphical options, sealing, viscosity, and so on and so forth. And once you're done with that, then you can actually start computing how the forces appears in a bearing. So these are just complete reaction forces, and as you can see here, there's like a shaft. On top of the shaft there's a mass, which is having the constant value of the force that is having the constant value, and then the reaction force is that is fluctuating here. And the fluctuation is due to the fact that the stiffness will be different in this situation when the force is traveling directly through the ball, or when the force is traveling through the two balls. And this is where the stiffness actually fluctuation is coming from. So even though that I have here ideal bearing, numerically ideal bearing, the fluctuation comes from the fact that even if the force is carried by one or two balls. And now this allows me to play with many different things. I can put here some initial forces and see how it behaves. I can introduce manufacturing idealities here, and I can play with either fatigue crack. All that is possible with this simple penalty force approach. So it's all about this one here. So penalty force, where I have here stiffness, penetration, and the n here is assumed to be 1.5. Now the penalty forces are easy to use. The problem associated to penalty forces is the fact that it's sensitive for integration settings, and it is very often used method. Now this item mentioned in the middle, and I need to explain it here. Why this is sensitive for integration settings comes from the fact that we all the time monitoring the penetration. And now you may think, okay, let me see if I can edit this. No, I cannot really move this. Oh, let me put another ball here. Let's look at that. I have here ball and how it comes to contact with this surface. Let's say that in a time equal to 0, the ball is here. And then I'm computing that ball dropping down. Here I can have one time step. This is a time equal to something else. And then I just got the phone call, so that's why it made me a bit confused. So this is a second time moment. So the ball is dropping a bit. And then I have one more time moment is coming down. And one more like this. Is not yet in a contact. And when I'm stopping my computing, I will take one more step, and it could be all the way down here. And now if you're assuming that these two, well, the crown and the ball are made out of the steel material, this situation here would produce a huge amount of forces because the penetration is of course unrealistic. And if this is the case, what will happen is that the ball will not bounce back to its original configuration that was roughly here, but it will bounce to all the way to moon. So that's why when using the penalty forces, you have to keep your time step small enough that this kind of large unrealistic penetration cannot take place. So meaning that you first compute it here, the second one should be here, third one here. So you're using very small time step to make sure that the penetration is not becoming unrealistically high. So that's the problem associated to this penalty force method. So it's sensitive for integration settings. And now let's go back to this one here. So I have here first in class quiz, and now I'm able to see how many participants I have today. So contact forces can be described using penalty forces. Drawback associated with this method is damping is difficult to describe, multiple contacts are difficult to describe, method is sensitive to integration settings. So Socrates is on. Oh, I can see 6 students, so it's not that low. No, not high either, but it's alright. So let's see how it goes. And while you're doing that, I will, while you're answering this question, I'm gonna check my phone. Okay. 9 students. Okay, this is actually a good number. Right? When I'm looking my YouTube channel, I don't see. I really don't know what's going on here. Maybe I need to go back to see what's going on in my recording. Yep, I can see that I'm live. Yeah, this looks good. And I see that, oh my god, I have 12 people following this. Yep. I mean 11 because I'm one also. This looks good. And hopefully there is not too bad echo. People following this. So, I mean 11 14 students. Oh, so the numbers are not matching. Too bad echo. Gonna wait a bit more. And then we're gonna look how is a complementary approach. Again, if there is a problem in my voice, I mean echo problem, please let me know, because you know it's very important that the recording is okay. So let me see if I got any. Please let me know, because you know it's very important that the recording is okay. Messages from your end. Not that I think. I don't think so. It looks alright. Not that I think. I don't. Okay, so 15 students. So it's becoming higher all the time. So 3 are still thinking. So soon I'm gonna close this, and then we're gonna move on to complementary approach. So 2 are still thinking, We are not, by the way, we're not going to have breaks today because I don't think what I will do during the breaks. I could walk here in my basement, but I don't want to do that. So I prefer just to go over today's material, and then we're gonna close earlier today. Okay, 2 are still thinking, but I think that I'm good to close this. We're gonna close earlier today. Okay, 2 are still thinking, but I think that I'm good to close this. Okay. So there was a proposal that the echo is coming from the fact that I'm watching my streaming. So now the streaming is off. So is this any better? Okay, so I'm ready to open this. So let me see. Is it going to be 100%? No, I don't think so. Well, it's possible. It's possible because, I only have 3 choices. 3 choices. So just doing the lottery, the chances to get 100% is quite high. So, without further ado, so the correct answer is that the method is sensitive to integration settings because it's all about the penetration. And penetration can be unrealistically high if the time step and integration settings are not properly selected. So that's the problem of the method. Multiple contacts are alright to describe, so it's not a big problem. The damping is alright to describe, so it's not a big problem, but the integration settings, that is a big problem. And now if you can let me know if how is my echo. How the heck it is possible that there is an echo, because I'm very carefully selecting that I'm just using the one microphone. I don't get it, like how this is even possible. But I see that there is quite a bit of background noise. That's at least what is a annoying thing. How is this? Is it? Okay, so it was somehow related to my streaming, so sorry about that. So I should not follow my streaming, so. Okay, thanks guys. Appreciate your help. Okay, so let's move on. So let's look at another subject matter related to contact event description. Okay, so don't get confused. So we still have the same big picture. So we are first making the contact detection. Contact detection is to see whether or not the contact takes place. If the contact takes place, then we have, roughly speaking, 2 choices to follow. So we can use a penalty forces, which is just forces that are separating 2 bodies away from each other. Or we can use this other approach, which is a cone-complementary approach. And now cone-complementary approach is a completely different story. So because now what we're gonna do is that we're gonna still following like how far from the bodies are from each other. But this is based on constraint equation, which is gonna be put in the form of inequality, meaning that bodies can do whatever they want, except they cannot penetrate. Meaning that, in constraint we can say, okay, I have here revolute joint, meaning that the bodies can move only relative with respect to each other, like here. Now, what we're going to do in the cone-complementary approach, we say that, of course, there is these constraints that are description of joints, but in addition to that, we have inequalities that are description of contacts. And they're saying the bodies can do whatever they want, except they cannot penetrate. So they can move like they want, but they cannot penetrate. So as soon as the contact takes place, that's when the constraint comes into place as well, and it's saying, okay, you guys get separated. So that's basically how it works. And it is a method that is typically used particle kind of bodies, because it allows to have a huge amount of contact to be checked simultaneously. And it being used in a wide variety of different applications. It comes with a certain computational difficulties, but it is an alternative technique for penalty forces. Now, without going too much into details here, basically how this method goes is that in two-dimensional case, we can simply have the inequality that is saying that, okay, this contact between the bodies are not allowed, and if they take a place, then we're going to have a friction that is going to be a function of these normal forces that is coming from the contact. This time is enough for you to know that, okay, this is based on these inequalities and it's kind of constrained description. So in that sense, it's very different than penalty forces. And it is typically used in applications like this one, where there's a lot of bodies that are connecting to each other. Modeling this by using bounding boxes, where each one of the balls can hit any one of the balls. This is going to be a lot of work to do, but with help of the complementary approach, this is doable. And it can account very much higher number of contacts than this. Now, here's my friend Dan Akers, and he's about to tell you a little bit about complementary approach. So now there is chance that things going wrong here in my presentation, because I need to put my loudspeakers on, because otherwise you don't hear Dan Akers. So let's see. Now look at this. Dan is not here to help me. Let me find him directly from the YouTube. So why this is not? Okay, I don't know. Cone. Here comes Dan Akers. This is too much.
Good afternoon. My name is Dan Akers. I'm an assistant professor at the University of Wisconsin in Madison, and I want to start by thanking you for taking the time to attend my presentation here. I'm going to talk about this topic of taking the leap from multibody dynamics to many-body dynamics. And let me first tell you what multibody dynamics is. In general, multibody dynamics looks, for instance, at the motion of this vehicle. In this case, this is a project that we have with the JPL, and you have a vehicle with a relatively small number of parts. What makes this a many-body problem is when you start looking at the granular terrain that the vehicle moves over. And in reality, what they're interested in, they want to see if this vehicle gets stuck in the sand. Now, in 1 cubic meter of sand, you have about 1.5 billion particles. And although you don't see this in this picture, in this movie, sorry, those small parts, they move. And you solve some equations of motion, and they come back to tell you at each time step that I don't move, I don't move, I don't move, I don't move. Once in a while they move, but nonetheless you have to solve at each time step a very large problem. Now, this is a simulation that is about probably 2 or 3 years old, and I showed it to some army guys, and one of them raised his hand and he said, so why is that Mars rover moving over potatoes? Are there potatoes on Mars? And this is my point. There are no potatoes on Mars, but you cannot go today to very small dimensions for granular material, because if you have, for instance, like a commercial off-the-shelf package, and you run a dynamics analysis, multibody dynamics, classical multibody dynamics analysis, with 32 balls dropping in that bucket, and you look at the time evolution of the system, it takes here for 32 balls about 600 seconds to understand the dynamics for 3 seconds. And not only that, but if you look at the shape of the curve, it's a quadratic function that describes this dependency, and a very quick back of the envelope computation tells you that if you have 1 million particles, it takes for 3 seconds the simulation about 25,000 years to run that analysis. And with all this Medicare discussion and cuts, I'm not going to make it that far. So we need a different solution here. So this is the solution here. We change the math behind the formulation, and this is a system that has about 1 million parts, and they're moving, and we're tracing the motion of every single particle and how it collides with any other particle in the system. And there's like a ball of a lower density material, and it floats on that. So here is classical multibody dynamics. I'm not going to get into details, but there was some math, okay, going from multibody dynamics to many-body dynamics. And once you take care of this problem from a different mathematical formulation, all of a sudden it becomes feasible, okay? And when it becomes feasible, then the next thing that you want to ask is, well, how close do the results come with respect to reality? And here we have like a silos, like a flat hopper simulation, and we ran that simulation, and then in the lab, we went and we took something similar. A graduate student, low salary, filled it up, painted the balls, and we did that simulation, and then you put them side by side, and here is what you have: experiment and simulation, and they look pretty much the same. And we did some other simulation, but I'm not going to show the results here. Of course, if you look at this problem, you have millions and millions of bodies that move. Now, the beauty of it is that basically they all move the same. So there is a lot of scope for parallel computing in this. And this is where you can use, for instance, GPU computing or multi-core computing. And this is what we did. And we implemented, for instance, here you have a system that has about 500,000 parts. And this is a project that we work for the Army. And we are interested in how the terrain deforms on a track vehicle. And it took about, for 18 seconds of simulation, it took about 1 day to carry out this analysis. Now, you can go beyond that, and I have to tell you that, I grew up in a communist country, and it was like, food shortages and such. So one of my recurring dreams was like, eating lots of chocolate. And here is it, I can say that I'm a happy man. My dream came true. Here it's like a virtual world. Like I have lots and lots of like chocolate here. Now the tricky part about this is that it is a simulation that combines multi-domain. It's a multi-domain physics simulation. It solves at the same time the Navier-Stokes equations and the Newton-Euler, and it's done in a parallel fashion. And if I were to conclude, this discussion, it boils out to one idea. There is a lot of computational power today, like parallel computing and such. It takes new math that you can map on that parallel architecture, and wonderful things happen. And with this, I thank you again for taking the time to attend my talk.
Okay, so that was my friend Dan Eckert. He said that he's from communist country. So too bad that we cannot communicate. Oh, I need to take this off because I guess this is causing some echo. It would be nice to organize a vote, like what is a country that he's coming from based on his accent. But I just need to realize that he's originally from Romania. So that was about how to use a cone complementary approach. Okay, so what is that we learned so far? So we learned that we have to use a contact detection method to see if the contact takes place. If contact takes place, usual way to solve that is using penalty forces. But we can alternatively use cone complementary approach, which is based on inequalities. And what the Professor Neckert was saying in his presentation was that this is another method that is no longer multibody dynamics, but he called it as a many-body dynamics. Many-body dynamics because we are speaking about, well, really many bodies, and the number of bodies that he's dealing with could be all the way up to millions. And now that there's a simulation where tens of millions of particles are interacting with each other. And of course, GPU computing is needed, parallel computing is needed, but still that's possible. So really a lot of particles are interacting with each other, so that's possible with the method that is based on cone complementary approach. Now, with that, let's move on and let's look at the another subject matter that I promised to discuss today. Another subject matter is about the stress analysis using multi-body system dynamics. And why is this important? Well, this is important because when we have a closed physics-based representation of machine, it can be used in a wide variety of applications, but it also can be used to support strength of materials studies, fatigue studies, and so on. And to make that happen, we have to be able to plot the strains, first strains and then stresses out from the models. And this sounds like an obvious thing to do, but in reality it comes with a certain difficulties. And what I will do next is that I will show you two ways to do the computing. One is really old-fashioned way, which is being used a long time and is still used. Another one is then more advanced, that is a way more sophisticated method than the first one. Now, basically, once you have your multi-body model ready, you have analyzed it in a different working scenarios, then what you can do, let me just close this to ensure that there is no echo. What you can then do in order to get the stresses out from the model is two alternative approaches. The first approach is something that you just take the forces that are applying in your model. That means all the forces. Reaction forces due to the constraints, inertial forces, all the forces that are applying, and you just take the forces, converted those to be input files to your finite element code. And then you're exporting those files or those information and put it in your finite element code and solving the deformation. And that makes it, if you do that, then it's possible to get all the post-processing tools that are available in a finite element software in your use. But of course this makes no sense, because you're kind of reproducing the situation, and you're producing quite a bit of time and CPU power to get the strains and stresses from your multi-body model. Alternative approach, which is really way more sophisticated, is to use something that is called modal stress matrix. Now, this comes together with the floating Feynman reference formulation we discussed earlier. Remember, in a floating Feynman reference formulation, we are sending modes, assumed deformation modes, from finite element code to multi-body system dynamics. But we can, in addition to that information, we can also send an information about how displacement and strains and stresses are related. That information could be combined to information package that is exported from finite element code to multi-body dynamics. So, and that's exactly what this modal stress matrix approach is about. But now let's first look at this first method, that is coarse, not very sophisticated, but still possible way to go. Again, so the idea is that you take all the forces that are applying in a system in each given time, and you're converting those forces to be externally applied forces to your finite element code. And because the body in any given time in a multi-body dynamics is in a dynamic equilibrium. So you can take these equilibrium forces and take them to finite element code, and then to solve equilibrium again in a finite element code. That makes it possible you to first get the deformation, and then once you get the deformation, well, displacement is a better word for that. Once you get the displacement, then it's possible to use this kinematic matrix that we discussed few weeks back. Take the kinematic matrix and estimate the strains from displacement, and then you can use material properties to estimate how much stresses are applying in your structure. So this is the method from beginning to end. Now, when you look at the literature from multi-body dynamics, this is a method that is sometimes entitled as a very sophisticated name. The sophisticated name is this. So it's called linear theory of elastodynamics. And this sounds like, really? So this is very, very nice. Yes, and yes, that's correct. So the title itself is very nice. Method itself is very coarse. So it's not very sophisticated at all. So this sophisticated one, how that goes? Well, it goes such the way that you first have your finite element code, then you take this deformation information about the deformation, you put them in a multi-body code, and then, excuse me, this was still the previous case, so you still take this information to to describe things in a flexible bodies, and then the force is coming back, and this is when you're comparing all the stresses. Now the modal stress matrix. This is coming directly to the theory of multibody system dynamics and the floating Fermi reference formulation. Well, in short, how it goes. It goes such the way that, this complicated equation here explains how is an equation of motion when bodies are described using floating Fermi reference formulas. So the variables we have here is motion of reference coordinate system, and then the modal coordinates. And you know that the modal coordinates are associated to nodal displacement with the help of this assumed deformation matrix. And now we just start following this track. So we're gonna check the p's that are modal coordinates, and from modal coordinates we're gonna get the nodal coordinates, and from nodal coordinates we can use more information, so we can look at how is the deformation of each one of the elements using this kinematic matrix, which here is denoted as a B. We can get strains, and using material properties, this is elastic coefficients. If there's other material properties that are needed, then you use those as well. And then from strains you can get the stresses. And now when putting all these packets together, so these elastic coefficients or other material parameters, kinematic matrix, displacement associated to one element, and then all the way back to modal coordinates, from nodal coordinates to modal coordinates, then once you put that in one package, you can call this as a modal stress matrix. Now, why this is nice? Well, this is nice because directly from modal coordinates you can get an estimation about stresses. That's what is here in the equation of motion. So equation of motion, you solve directly p's that are modal coordinates, and as a post-processing technique you can have an estimation about stresses. So that's how it goes. So here's the summary. So we can use the first approach, which is a very coarse, still usable. And in that first approach, we take the forces from multibody code, we put these to finite element code, and in the finite element code we're comparing the deformation, and once we have a deformation, then we can get an estimation about strains and stresses. It's mentioned that is a CPU consuming approach, and that's what it is, but still doable. Or we can alternatively use this modal stress matrix, and this is very efficient. Only problem is that this is about two different software. And sometimes, even though that this is theoretically so much straightforward, sometimes we don't have an access to that information. That really depends what are the two softwares you want to put together. Now I can see that the lecture being on already hour and 10 minutes, and I think that today's lecture is designed to be hour and 30 minutes. So I'm thinking that I'm still gonna go ahead and explain things related to fatigue analysis. Not going too much into details, but providing you a little bit of overview about fatigue and how multibody dynamics can be used in a fatigue analysis. Now this story is not long story, but is looking first to fatigue perspectives. What I do here when I'm explaining things in a fatigue perspective is that I'm not going to narrow myself to discuss about welded structures only. And of course, that's a big limitation, but welded structures, because LUT as a university is specialized to fatigue analysis, but mainly the fatigue of welded structures. And another reason for that is a practical reason, because when you look at most of the structures, heavy machinery, heavy mobile machinery, those structures consist of elements that are come together by welding. Now the welding is there, so is that multibody dynamic comes into play, and how that can be used as a part of the fatigue analysis. Okay, so let's go. So what is needed in order to make a fatigue prediction? And the first thing to know about the fatigue is that it is statistical phenomena, and that's good to keep in mind. So it's not that you can say exactly when a structure will break, but they will be distributed statistically, so we can have a certain certainty, certain threshold value, a certain clearance about when the structure will break, and we can give these statistical values. Although that today I'm going to explain about more exactly, like this is when things are going to be broken, and it's going to be broken because of this and that. But strictly or generally speaking, fatigue prediction can be carried out once we know about geometry, which is like what is a detail we're looking at, what is a material we're dealing with, once we know the loading. And this is actually something important for us because geometry is often something that is known. We know what's the geometry. Material for sure is well known, but the big question mark is typically how is a loading that is imposed to structure. Because if we're dealing with a structure that is not yet existing, it's very, very difficult to get the loading history. A loading history, the only real way to get it is by using multibody simulation. And that's why these two subject matters comes together, fatigue and multibody dynamics. Now, fatigue resistance, durability can be defined when you know the geometry and material properties. And then we just need to know the loading prediction, and that's typically the most challenging task that one needs to carry out when doing the fatigue prediction. Fatigue itself, this is only when we're speaking about the welded structures. It consists of kind of three phases. Well, the one phase only is the real one. Others are almost non-existing. Well, in order to be, the fatigue, what that is, that's a crack propagation. It meaning that we have a small crack that started to grow within the structure. And the problem when we're dealing with the welding is that it is a fair and good assumption to consider that the welded structure, because the welding process itself will introduce smaller microscale cracks within the welded toy. So when you look at carefully, really careful about the welded toy, it is a fair assumption to say that there is already initial crack in the structure. Even though that we are dealing with a brand new component that is welded together, or one brand new product that is welded together, it is a fair assumption to say that there is an initial crack in the structure. And that's because of the welding process. So welding process will introduce this crack, even if you would like to be very careful. Now the real fatigue life is all about the crack propagation. So how the crack is growing in the structure, and as it becomes long enough, then what follows is a final fracture. Now the final fracture takes place in a fraction of the second, of course, and that's when these two components will be separated. In welded structure, the one that is dominating, the one that you need to look at is of course the crack propagation, this crack growing phase. That's the one that is only the important thing, because you can consider that there's initial crack in the structure, final fracture will take a fraction of the second, but this is a time that takes the most of the time, or this is a phase that takes the most of the time. So now let's take a look at this. So in welded structure, the fatigue life is dominated by, from these phases, crack initiation, crack propagation, final fracture, the one that is taking the most of the time. Let me put my Socrates back on. Not that. This one. Next. So I have still my 15 participants. Okay, now the answers are coming. So there's only one answer. Is it this because of having difficulties in my streaming, or what's up with this? Not looking very promising. Oh, no, more is coming now. Okay, good. Very good. Okay, so slowly it is becoming. Now I have 6 answers, 7. Okay, so it's increasing. I guess this is because of the delay in the streaming, I suppose so. And of course it needs a little bit of time to think, how is this thing? So I have 11 answers already. So soon I'm good to close this. And then just one more thing, and I will close today's lecture. Let me see if while you're answering, I'm seeing if there's any messages from your end. Okay. Okay, 13 answers, 14. Okay, so is it going to be 100%? Last time we got 15 answers. So let's see what's going to be score from this one. So let me close this and move on to rest of my explanation. Nice. Crack initialization is something that is important in case of unwelded structures, but this is about welded structures. So in welded structure is a fair assumption to say that there is initial crack in the structure. Even though that is a brand new structure, initial crack is there. You know, what happens because of the geometry is that there will be many different stress of this geometrical nonlinearities, that when you look at it very, very closely, the stress itself becomes quite high because of these geometrical nonlinearities. This is something that we will get back next week, so I'm not going to explain this in very much in details. But I'm going to just say another problem that is associated to welded structure. So again, welded structure are problematic and vulnerable to suffer from fatigue because they consist of initial cracks. So that's the first problem. Another problem is that the welding process itself, when you look at the welded toy in very microscopical scale, in very low scale, detail scale, there is a very high residual stresses because of the welding process itself. So now if you go to say that, you know, this is two components that are welded together, this one here is a weld. If you look at like what are the residual stresses in this particular location where the crack is growing, it is fair assumption to say that, you know, the stress in that particular detail is actually very high. It's actually in a phase when the, you know, the linear behavior turns out to be nonlinear behavior. So this is a curve where I have strain stresses. So this is that famous curve where it's telling how the material is behaving. This representation is typical behavior for steel material. In the steel material, once you're loading your structure, the strains will increase, stresses as well. Once you reach this point, everything is still fine. And once you release your load, the structure becomes back to origin of this curve. When you're increasing the force from here, from the linear range to nonlinear range, this is where the plastic deformation comes into play. And now if you go all the way here and you release your load, you're not going back to original undeformed configuration, but instead you will have some permanent deformation. This is how the structure behaves in a big scale. Microscopical scale, when you look at the welded toy, this particular detail here, it is fair to say that the residual stresses due to the welding process are pretty much in a phase when the linear phase ends and the non-linear phase starts. This is when the permanent deformation takes place. Now this is good to keep in mind, because as soon as you start loading, as soon as you start going ahead from this curve, you already step to non-linear phase, which is meaning you're introducing locally, very locally, permanent deformation to your structure. That is crack propagation. Now, why this fatigue is a big problem, even in the case if you want to use a high-strength steel, is the fact that, because of the welding process, the residual stresses, pretty much all the case will be in this phase when the linear turns out to be non-linear. Now, if I have here closely, very nice high-strength steel, the residual stresses will be just higher, because of the welding process itself. So it's not going to help me much, because now if I'm going to load the structure, similar way that in the previous case, I'm going to move on here to this nonlinear phase. Here to nonlinear phase. And that's what makes it possible to crack the crow, even if you're using these high-strength steels. So that's, in summary, that's the two big drawbacks that are associated to welded structures. So let me summarize those again. So welded structure is a fair assumption to say that there's initial cracks in the structure. And that's because of the welding process itself. And then it is a fair assumption to say that the residual stresses locally, very locally, in a location where the crack is growing, it is pretty much high in a way that as soon as you start loading the structure, you step to this nonlinear phase. And this is when it is possible that the crack started to grow in your structure. And that's why the high-strength steels are not really helping you too much in terms of fatigue. Alright, so that's where I'm going to close today's explanation, today's lecture. So we'll go back and check how was quality of my recording today. And then next Monday, same time, same place, I'm going to wrap up the topic of this fatigue, and then we're going to discuss a bit something else. And then, let me think, is it like one more lecture after that? And then we're done. And then there's just a midterm exam. And then we are ready to close this course. And I know that this is a very special time and you guys are facing many difficulties. But please communicate with me and Bertu. And if any difficulties, let us know. We are as flexible as we can. That meaning that we are very flexible. Alright, so with that, I think that I will close today's lecture. You guys take care and see you on Monday. Same place, same time. See ya.